Question number 3 on the Prof. Miller handout is a rather more classic E1 elimination type setup. We have a substrate that has a relatively bad leaving group, say an alcohol, and so we're going to add to that sulfuric acid, which has the tendency to make this into a better leaving group while providing no nucleophilic anion. There's no nucleophile present here. And then he's also adding heat to the reaction, which tends to drive things toward elimination. So these are signs that we're trying to run an elimination reaction. If you're trying to figure out the mechanism of how this works, what you then need to do is draw out the Lewis structure for the sulfuric acid in order to see how this goes. This oxygen right now is a relatively bad leaving group, but it has electrons, so it can serve as a nucleophile, pick up a proton from the sulfuric acid, which then leads to the sulfate anion. So what we end up making here is going to be the protonated alcohol, which is now capable of leaving. Again, it is always my advice that you should draw out these hydrogens explicitly so that you can then use them in future steps if you need to. Although in this case what happens is the water simply leaves, which leads to this particular cation. So again, equilibrium step, the water can leave, the water can add back in, we can go back the way we came, and so on and so forth, but we now have water floating around down here. By the way, the other byproduct from this is hydrogen sulfate anion, but this hydrogen sulfate anion is not going to be participating in the remainder of the reaction. It is the conjugate base of a strong acid, so it won't serve as base, and this oxygen, because it doesn't have much charge because of the resonance, this is really non-nucleophilic. So this is just a spectator from this point forward. Okay, so what could happen at this point is, of course, the alcohol could add back in, and you could end up going back the way you came from, but there's also hydrogens bound at this position, so you could imagine one of these hydrogens becoming abstracted in order to lead now to a new product, and so one of the things that you're going to form is the elimination product, which in this case we would describe as being sort of a Hofmann style product. It ends up being the less substituted double bond product that we could end up making. This is, of course, the kinetic product. Notice that there are no hydrogens at this position, so there's no possibility of abstracting a hydrogen at this position over here. However, this is now possible to slide over. What we have here is a secondary cation, which means that we could in fact go ahead and form a tertiary cation by doing a methyl shift, which then leads to this intermediate, where we now have two methyls. At what was this position, we did have a cation. Now that is totally content. Where we were left behind, we now have a plus. There are still hydrogen atoms present at these locations, so it is possible that we could do a elimination here, pulling off one of these hydrogens to kick down to make a double bond, and this likewise would be a version of a Hofmann product. You could also make this double bond, and this would be a Hofmann product that first results from rearrangement, carbocation rearrangement, and then deprotonation. And this also would be a Hofmann product because, again, it is the less stable possible outcome. However, there is also a hydrogen present at this location right here, and so we could imagine that the water could deprotonate this hydrogen, and if it did so, that would then lead to what we would describe as the Zaitsev product. These E1 eliminations are almost always going to lead to a significant mixture of products, and that's because basically anything can happen. You don't have a nucleophile present, there's nothing that drives this reaction forward. This thing just kind of floats around and falls apart when it feels like it. You would imagine that there would be a strong preference for the Zaitsev product because that's the lowest possible energy product. And that's true, but the problem with that thought is that this cation is really a high energy intermediate. It does not want to exist. And even when we turn it into a tertiary cation, it's still a relatively high energy intermediate. And so this won't exist for much lifetime if possible. As soon as the water can come by and abstract a hydrogen, it will, and the water is not going to be particularly sensitive to whether it abstracts this hydrogen, making a Hofmann product, or one of these hydrogens, making a Hofmann product, or the correct hydrogen in some sense, the one that leads to the most stable thing, the Zaitsev product. These E1 elimination reactions tend to be fairly unselective. They're not entirely unselective. You might imagine that we would make more of the Zaitsev product because it's lower in energy. On the other hand, it's also entirely possible that we make more of the Hofmann products because there are simply more hydrogens possible to be abstracted. And here's a case where those statistics are probably going to matter a little bit. Assume that these are going to be relatively unselective reactions.